Morning, everyone. Good afternoon, everyone. Welcome to the seminar series. In particular, thank you to Dr. Thomas Montenegro-Johnson from the University of Birmingham for joining us. Dr. Montenegro-Johnson is, is a senior lecturer at the University of Birmingham in mathematical biology, although his research fields extend into mathematical biology, continuum mechanics, and soft matter. Dr. Montenegro-Johnson, thank you for joining us, and I'll pass over to you. You can begin when you're ready.
Lovely. So firstly, thank you so much for having me. I really wish it was in person because, you know, Cyprus is on that kind of to visit list of places, but hopefully we can do that at a later date. He says inviting himself mid-seminar when no one can object. So I wanted to start by just giving you an overview of the group, me, who I am. This is a photo of me from before I had kids. You'll notice that I look younger and more energetic. And here I've sort of divided this into projects. So in the first column, I've got my Leverhulme Research Leadership Award project, which sort of started in December of last year, and that's going to run for 5 years. And I've got 3 really good research fellows on that. Armin Ramat, who's sort of does smooth particle hydrodynamics, that sort of stuff. Azar Shirazi, who is going to be doing some 3D printing of soft hydrogels, thermo-responsive hydrogels. And Matt Butler, who's my replacement Panayotta, really good theoretician with a sort of strong academic math background. And at the moment, we've got one PhD student, Burke, who's doing really well at the moment. He's working on a paper with Juliana Simchen's group in Dresden, if you know them. And we're recruiting a couple more PhDs and one more research fellow to be advertised towards the end of the year. If you know anyone that is interested in the sort of, in the field of soft matter, I'd be very happy to hear from them. This is funded by the Leverhulme Trust, this bottom thing here. And then, as I was saying earlier, I've got some other projects as well. H-Reality, which is a Horizon 2020 FET. And that's with Orestes Georgiou, whom some of you know. The research fellow on that is James Andrews. He's sort of coming towards the end of his contract now, but we're trying to renew. And that's all about, well, my part of it anyway, is about understanding the mathematics of the sense of touch. So that's a really interesting kind of soft matter sort of tissue physics problem coupled with some sort of network theory of information propagation through nerve networks. It's some really interesting stuff, and we're making some good progress there. Finally, some of the stuff that I'm going to talk to you about today was an EPSRC funded project which Panayotta, whom you all know, was hired on, and I understand she's going to give you a little bit more detail and stuff further on than the stuff that I'm going to talk about today. But I'm going to be mercilessly exploiting some of her research and passing it off as my own throughout this procedure. So I'll point to you when we get to Panayotta's amazing work there. PhD student Matt Close started sort of before all of the funding. He is working on algal colonies. Okay, so a little bit of overview of current research. The idea behind this shape transforming active microfluidics is to 3D print folding origami structures using sort of composite thermo-responsive and non-responsive hydrogel structures to functionalize devices, microfluidics devices. And that's sort of in collaboration with a company called Cellink, who are based in Sweden. They're really cool. The H-Reality project on touch that I mentioned, funded by the ERC, and that's in collaboration with these universities and Orestes' company Ultra Haptics, and also Actronica, who are a Paris-based haptics company. While I sort of started working on started my academic career working on propulsion of microorganisms, of sperm and what have you. I also got into vertebrate symmetry breaking and artificial microscale propulsion. So vertebrate symmetry breaking, a very interesting problem whereby the vertebrates choose where to put their asymmetrically placed internal organs. So for instance, in humans, you have the heart on the left and the liver on the right. And this is actually mediated by a cilium-driven fluid flow. So it's a fluid mechanics problem. I've got the microtransformers project, which I'm going to talk to you a little bit about later, which is about using shape responsive materials to create run and tumble micro swimmers. And we have an exhibit of that in the Birmingham Science Museum. If you're ever visiting, go up to the top floor. That should be around for the next 5 years or so. And we've recently sort of started a bit of work into topological active colloids, so non-point-like particles. And I'm sort of going to be focusing on these bottom two things here today. Okay. So today we're going to talk about some modeling, simulation, and experiments. And the sort of the unifying theme here is that we're doing active particles, but they've got very much sort of a non-standard shape or topology. So it's what happens to an active particle when it's not a point, it's a donut. So we've got the autophoretic torus there. What happens to active particles when you elongate them to the point that they're effectively filaments and you start curving them in 3 dimensions? Well, that's the work that Panayotta did. And finally, I'm going to talk to you about a sort of early experimental realization of some of these filament microswimmers with these bubble bots towards the end. Okay, so microbots. What are they and why do we need them? So the idea is that you have essentially the idea is that you have to find a way to propel yourself in the microscale environment, which means overcoming a drag-dominated regime. And lots of the ways people have decided to do this is by copying nature. So probably the first realization was by Dreyfus et al., who took little magnetized beads in a particular direction, glued them together at a sort of a different angle of the magnetization, put it in a rotating magnetic field, and you get a sort of nice traveling wave that imitates a sperm-like motion. That's probably an oversimplistic version of what they did, but that's more or less it. Then you have sort of some biohybrid designs. So this Maggie et al. Paper from Small, what they did was they took a filament of PDMS, and around this little area here, they got some heart cells, cardiomyocytes, to bind and put it in a nutrient bath. And because the heart cells contract, you get a sort of local bending around here, which propagates a traveling wave backwards, and because of the way that it's set up. And that leads to a net propulsion. And here is the last example I'll talk about, a rotating, a helix with a magnetic head put in a rotating magnetic field. And this is a sort of artificial bacterial flagellum. The magnetic field rotates it around, and because you're at microscopic scales, rotation is coupled with translation, and the thing moves more or less wherever you want it to. And there are other examples. And there are sort of many potential uses. The most romantic, I suppose, of all of them is this idea that you might swallow the surgeon, as it were, as Richard Feynman put it back in the 60s. The idea that somehow you could swallow some of these microbots and they would go to work and heal your body from the inside out. That is a eventual desired goal of these microbots. Obviously, there are lots of things to get over. Other applications are cargo transport, enhanced mixing in microfluidic devices, and a few other things of that nature. So moving on now, what I'm going to talk about mostly is chemical propulsion. Now, I warn you, I'm not a chemist. I'm a mathematician playing with a box of toys in a sandpit. But I do welcome comments as to how simplified the chemistry of all of this is. So a sort of a classic autophoretic swimmer would be a point-like Janus particle. So what you have is a polystyrene bead, and it has a platinum, it's half coated in platinum. And you place it in a bath of water with some dissolved hydrogen peroxide. And the platinum catalyzes the reduction of hydrogen peroxide into water and oxygen. And this generates a local self-generated gradient in the solute concentration field, which drives propulsive slip flows, which makes the thing move along. How does this work? Well, if you have a homogeneous particle, you have, so this would be a fully coated bead. The molecules of solute interact via short-range potentials with the particle boundary in a thin layer that is much, much thinner than the radius of the particle, sort of around 15 nanometers, and nothing happens in this case. You don't get any kind of propulsive slip flow. But when you have inhomogeneities, for instance, a self-generated gradient, you have different normal pressure gradients, different parts of the surface, which cause a tangential pressure gradient, which drives a slip flow, which can be characterized by a slip flow that is proportional to gradients in the surface concentration of the solute, which arises from a chemical activity, which is given sort of by a constant flux condition or something more complex. Here I'm just going to be talking about constant flux conditions, which isn't a terribly good model, but does allow us to make some progress. So what influences the trajectory of such a swimmer? Well, what we do is we solve Laplace's equation for the solute outside, assuming 0 Peclet number, so quite a small swimmer. And then we calculate the slip velocity from the surface field gradient, and that becomes a boundary condition for a Stokes flow problem. So things like particle design affect how confinement changes solute dynamics. It also directly influences the solute dynamics where you pattern the chemical. And this creates a slip flow that feeds into the hydrodynamics. And then also you've got to take into account things like wall attractions, sort of geometric confinement of the environment that you're in, and whoops-a-daisy, affecting the hydrodynamics. And so from this, even though you only have a one-way coupling in this 0 Peclet limit, you get some quite interesting emergent behavior, and some quite complex equations to solve, as Panayotta will tell you. So the first thing that we did was, well, we wanted to consider what the simplest type of swimmer that had natural geometric confinement in was. And so the simplest thing we could think of without, in free space was a torus. So we decided to consider axisymmetric chemical patterning within this framework. And very fortunately, I won't bore you with all this, but Laplace's equation is separable in toroidal coordinates, which means we can simply write down a solution as a sum of Legendre functions of the first and second time with half integer degree. So it's a bit like, this is a bit like a Fourier expansion of our unknown solution, except we're in toroidal coordinates, so we're using a Legendre expansion. And then you can apply the condition of the Neumann boundary condition to rearrange. And from that, we can then differentiate and get a series for our slip flow. And then what we do, because Stokes is a bit gnarlier to solve, we actually have, there's a paper by Leshansky and Kenneth where they solve the Stokes. And so we have a sort of a semi-analytic solution for the axisymmetrically chemically patterned donuts in free space. And so after doing all of that hard mathematical work, I simply put it into my boundary element code, which was a lot quicker and easier to set up. And we see that we get very good agreement between the analytical solution and the boundary element solution, which is great. So what do these fields look like? Well, because we've got this is a uniform autophoretic torus, and because we've got constant confinement on the inside, this is the solute product field normalized somehow. I can't exactly remember. And so you have higher solute concentration, product concentration on the inside because you have a fixed flux all the way around. This leads to a tangential gradient in the concentration from the inside to the outside, which drives a propulsive slip velocity. The maximum of the flow speed you can see is here, and whoops-a-daisy. And so what this particular swimmer does is it pulls fluid in from the sort of polar from down here. It pulls fluid in and then pushes it radially out. So it acts a bit like a stress slit, if you know what one of those is, a point stress oriented perpendicular to the torus. So the uniform chemically active torus does drive a slip flow, unlike a uniform sphere, but it's a pumping flow. The thing doesn't swim. But what we can do is, because it's a pump, we can look for the optimal pump, which for a given fixed surface area. And this is what the optimal pump looks like here. And you can see a fatter version here that's suboptimal, and a thinner version which is also suboptimal. Moving on, you can chemically pattern the surface so that you get a sort of Janus torus. And in this case, you have a very similar, the confinement gives you a very similar signal. It's stronger on the inside than the outside. But now you'll notice that the bias of this higher, this is no longer up-down symmetric in Z equals 0. The high product concentration is biased towards the catalytic side, as you'd expect. And because of this, we now have a swimmer, and we have flow that goes through the middle of the donut, and a dividing streamline here, which is dotted, and flow that goes around the outside of the donut. And again, you can come up with optima for whatever sort of patterning you want to think about. And crucially, what's interesting here is that you have for different patterning, you have different donut shapes. What you have to realize is that here we're also optimizing for minimum drag. So there's not only a maximizing the surface slip velocity, which comes out of sort of maximizing this gradient in concentration, which you might expect D to do very well, but we're also trying to minimize drag. Okay. So that's all fine and theoretical and lovely. We were very lucky that Igor Aronson, with his then PhD student Remy, decided to want to make some of these for us. So that they contacted us, and yeah, they used their nanoscribe to 3D print some little tiny swimming tori, which was really cool. So okay, we made these, and we made a glazed version. Here you can see this diamond ring. This is a glazed version where you have an inactive side up and an active side up here. So it looks like a little diamond ring, which is cute. And here we have a dunked donut, where you have this sort of active catalytic layer and a non-active. Can you see my cursor, by the way? I'm assuming you can see my cursor. I'm waving it around all the place.
Yes, we can see it.
Okay, that's good. What we did was we put these donuts, they fabricated them with a nanoscribe, I think that was on the slide. We put them in hydrogen peroxide solution, and what they did was they sort of glided along the surface at a bit of an angle when they were glazed. The smaller donuts swam at approximately the same speed. So we were in the limit where the limit of 0 Peclet number, and they swam at an angle of about 15 degrees. But because we also had the nickel binding layer in these, we could put a magnetic field in, and that would flip them perpendicular to the boundary, and then they'd swim very fast indeed, about sort of 16 microns per second, which is pretty good for these swimmers actually, given they're a sort of 7 micron radius. So the lesson from that was that gliding tori, the ones sort of going gliding at 15 degrees, use a significant portion of their thrust just in order to hover above the boundary. And it's also harder to translate if you're near a boundary. So that's why they were so much slower. They formed some really interesting bound states, dimers, trimers, clusters. You know, they'd form little dancing pairs, if you like. They'd come together at different angles and rotate around, doing a sort of waltz-like behavior, which was really nice. So there was lots of kind of collective dynamics that we're still exploring. This is all published in Nature Communications, if you want to take a look. So what did I do? Well, here's the simulations. These were done with a code which is mostly freely available. I haven't updated it to the latest version yet, but it's a regularized boundary element method numerical code for solving phoretic problems. And so we put the torus above the boundary and saw that it did indeed hover. And it had a different hover height depending on density and what have you. But this is where the problem set in, because if you started the donut tilted at an angle, in the classical sort of mathematical framework that we had, it would sort of then sort of glide and reorient itself so that it was perfectly perpendicular to the boundary, perfectly parallel to the boundary once more. And that said that we were missing some fundamental physics, and we knew that we were in a 0 Peclet number limit. And then we realized that because we had this nickel layer, we had some electrical, some electrostatic instability, and actually we had charge flowing across the surface, and we had this lower surface was also charged, and if you put that back into the simulations, then you can recover this sort of 15-degree gliding mechanics. So that's nice. The really fun thing about them, though, is that because they're charged, they can differentiate between particles of different charge. So here you can see that this little Roomba or Hoover has managed to pick up loads of negatively charged particles in front of them, and it's just carrying them around. And this one here, well, because it's moving forwards, the back is negatively charged, so it's picked up one positively charged particle compared to this large number of negatively charged particles. So that's nice. So there's some potential for them to sort of sort through heterogeneous mixtures of particles and collect things up. So that's quite nice. One of the things that we also demonstrated was that they exhibited active transport. So they transport bacteria, which was a happy accident of having not quite a clean room. And we also noticed that they were able to transport bimetallic active rods in two manners. On the left here, you can see the mothership mode, where the rods sort of attach themselves and the Janus Taurus glides along like the mothership from from Independence Day, and then you give it a little tap and all the Janus rods go free. And then the other mode is what I call the Pied Piper mode, where you're holding, using a magnetic field, hold it perpendicular to the boundary, and the rods sort of flow through the stream, through the hole in the middle, and sort of follow behind. Okay, so that's it for the torus work. I'm aware of the time. What I wanted to also talk to you about was Panayotter's work. So the torus is sort of the easiest way, mathematically speaking, to put geometric confinement into this problem. But the next thing that you can do to give yourself more freedom than a point-like particle is just extend it. Extend this to the point that it is no longer a point, which has 0 dimensions, but is now a line which has 1 dimensions. And you can then curve this 1-dimensional manifold through 3-dimensional space. And then we can generate all sorts of confinement and geometric interactions. So this was work done by Panayotta while she was my postdoc on the EPSERC project. We also had Seb Michelin as a collaborator on this work. You can read about it in the Journal of Fluid Mechanics. You'll there in the appendix you'll see all of the work that Panayotta put into some very difficult mathematics. So it's a fun read. We have essentially the same problem here, a fixed flux boundary condition that varies across the surface. So for instance, on these red particles you'd have flux, and this black part you would have no flux. And then you solve Laplace, it gives you a slip equation, and then you solve Stokes. But crucially now, we're going to rely on the fact that we're slender. So we've extended to 1 dimension, and as most of your computer people, you'll know that simulating anything where you have a difference in length scales means that you end up having to resolve a very fine length scale and a very large length scale, and that's very inefficient. So if we want to do things like fluid structure interaction, we need a slender body theory for this. And the great thing about slender body theory is we can do these fluid structure interactions, and we can also extend that to suspension dynamics. So the real problem, though, with generating a slender body theory is that the slip velocity for our problem is given by surface gradients of concentration. And so, you know, if you have no azimuthal variation in patterning, you have a very small azimuthal variation in concentration. However, because you're very, very slender, your gradient in that direction is hit by a 1 over the slenderness. Okay, this 1 over the radius, effectively. And so that means that these very small variations in azimuthal concentration have a leading order effect on the dynamics. And that means our slender body theory needs to go to first order. Well, what does that mean? Essentially, what we have is a parameterization of the filament in the Serre-Frenet coordinate system. So it's a 3D parameterization of the filament that preserves arc length, which gives us a surface element of the filament, which we're going to need to then put, which is quite a complex expression. We don't need to go into it. We put this surface expression into our boundary integral equation for Laplace. So what we do is we start off with our boundary integral equation, which is fully 3D. It takes the problem of solving the fully 3D bulk concentration and reduces that to evaluating an integral, well, solving an integral equation on the surface of our swimmer. And then what we do is we take little elements of that surface, these ds by ds, and and that is relying on the fact that we have, so this is still exact. We've got these surface elements exactly, and then we rely on the fact that we're slender to reduce this surface equation into a single line integral. So over several pages of substantial work, the leading order concentration is given by, whoopsie-daisy, is given by this top bit here. And you see what we have is a line integral from its s equals -1 to 1. This here looks complex, but essentially it's a point source, so 1 over r, a point source in Laplace's equation, weighted by the activity, so the chemical activity, the flux condition, and the local radius. And this here is a desingularization of this integral, part when s prime equals s. And this bit here is just sort of the local contribution that you get from this desingularization. So essentially you can think of this as crossing out this part and crossing out this part. To leading order, what you have is a line integral of sources weighted by the radius and the activity. These angular braces denote azimuthal averaging. And we also, if you have some azimuthal variation, then you have this integral from -pi to pi of this activity term as well. And actually at leading order, if you have azimuthal variation, at leading order, this term dominates the dynamics. The azimuthal term dominates the dynamics. However, when we're making these sorts of things, it's probably more likely that we're going to have some sort of long filament and we're going to dip the ends, in which case we'd have activity A of s theta that is just A of s. And when we do that, we recover just this part at leading order. And you'll see that all we're doing now, instead of solving a 2D integral equation, we're evaluating a 1D line integral. So it really is, it's for typical problems that we want to look at, it's around 3,000 times faster, I think, more or less, the whole process. What we then do, though, if we're doing axisymmetric chemical patterning, what we then need to do is go a little bit further. So this is our 0th order solution, and then we have to first order in the slenderness, where epsilon is the slenderness parameter. We have a term here that represents the confinement, the fact that you have local curvature. If you're sort of curved locally, you have a bit more confinement this side than this side, and that is going to lead to azimuthal variations in the concentration. So that's what that represents. This is a desingularization that integrates out to this term, and this sort of term that is proportional to 1 over r squared, because there's an r naught up here, essentially works out as a line integral of dipoles, so a line integral of source dipoles. So that's the full equation, and still we're evaluating a line integral. Okay, so that's fairly gnarly. What can we do with it? Well, we can do whatever we want. We can do different N shapes, different 2D shapes, straight circular arcs, S-shaped swimmers, and helices, and different chemical patternings such as Saturn particles, Janus particles, uniform particles. We considered all of these. First, we validated against an analytical series solution for a prolate spheroid, a Janus prolate spheroid and a uniform prolate spheroid, and we found that the error in our Slender solution decayed like the slenderness squared, which is to be expected from our theory. And here you can see, well, I'm not sure which is the analytical solution and which is our Slender solution, but it doesn't really matter because you see that they agree with each other very nicely. So it works. It works in the sort of the straight case. What about azimuthal variations, which is all the point of this? Well, comparing against boundary element methods, we got very good agreement for circular arcs and S shapes. And then we can take that a little bit further and say, well, do these azimuthal variations have a leading order effect? And actually, as you can see here, I believe dashed lines do not, whoops-a-daisy, dashed lines do not include azimuthal slip flows, and the solid lines do. And for a uniformly active circular arc, if you don't include the azimuthal slip flows, you're actually predict the incorrect swimming direction in certain parameter cases. So it really is a sort of leading order importance, or in this case, you predict the incorrect rotation direction. Finally, what you can take this into 3D, look at a Janus helix, and you can see that they as sort of a helical active particle undergoes a helical trajectory with the sort of the parameters of the trajectory depending on various geometric parameters of the helix, which is perhaps not surprising, but certainly cool. Okay, so the final thing that I want to talk about in the last 10 minutes is the sort of so what where all of this is going. Well, what we're trying to do now is make composite filament-like swimmers out of hydrogel, where you sort of have a sort of blue. The blue here is a non-responsive hydrogel, and the yellow here would be a thermoresponsive hydrogel. And then by sort of stimulating this swimmer, you can get this yellow bilayer, yellow part of the bilayer to contract and switch between a translating mode, in this case, and a rotating mode. And then you can use this sort of localized stimulus-dependent shape change in order to have selective control over your micro swimmers. So for instance here, if you wanted to send this magnetized swimmer around this corner, you could do so by varying your magnetic field, but this swimmer would crash into the wall. Whereas here we can use our localized shape change to send the swimmers off in different directions without affecting the others. That's the theory anyway. And you do some simulations, and you see that it roughly works, which is great. And you don't really think much of it until someone useful and practical decides to make some for you. So this is work with Ivan Rahor and Juliana Simchin. Ivan's in Prague and Juliana's in Dresden. They made some hydrogel I, U, and S swimmers with an enzyme that catalyzes the reduction of hydrogen peroxide in the ends. That's the red bit, and just ordinary hydrogel here. We haven't quite made the thermoresponsive, the shape change bit here, but what we see is that these swimmers do indeed behave more or less as predicted by the theory. So the U-shaped swimmer here swims at a more or less constant speed and doesn't rotate. The I-shaped swimmer here doesn't rotate and doesn't move, but it does pump flow. You can see particles being drawn in here and sort of pushed out in a stochastic manner. And the S-shaped swimmer, due to it rotates very nicely at a more or less constant speed, but it does also precess slightly, because it's very hard to make one of these completely perfectly. So our S-shaped swimmer in this case is not a pure rotor. So what you notice here is that instead of sort of classical autophoresis, the reactions that are taking place here are causing the oxygen to sort of nucleate into a bubble, and that bubble grows and then cavitates. So this is bubble propulsion rather than autophoretic propulsion, but essentially being made from the same components. Generally, if things are a little bit bigger, you end up with bubble propulsion and not autophoresis. But I don't believe the sort of precise boundaries of that have been worked out yet. So what did we do? We looked at this bubble growth and used automated image analysis via a circular Hoff transform to extract the bubble radius as a function of time, which you can see here. And that allowed us to look at things like how the maximum radius of the bubble decayed for different bubbles with time. This is to do with the enzyme becoming denatured by the hydrogen peroxide, and also check sort of bulk properties such as the fact that the cavitation events are getting longer and longer apart as the experiment runs, again due to this enzymatic denaturing. We're also able to fit the experimental data to a model. And we created this model by starting with the ideal gas equation. And from that, we can take the time derivative of both sides. dN by dt is the sort of the molar flux, to see how the rate, and that sort of allows us to check how the radius is changing. This is the volume of a sphere. This is the Laplace pressure. And what we did was we assumed that, well, because we've got this catalytic surface that is generating generating product at a more or less fixed rate on the timescale of the bubble, we're going to assume that the molar flux from this surface into the bubble is constant. We're basically assuming that all the interesting stuff happens at the surface, happens at the catalytic surface right by the bubble. And if we assume a constant molar flux Q, we get a one parameter fit model and this implicit equation for R as a function of T, which is reasonable, not too horrible to look at. And then we can do a sort of take all of our phases of bubble dynamics, create an average. And I lied to you slightly. We also generated some other models, but they were no good, so I didn't bother showing you. As you can see, the fixed flux model works really beautifully here. This is a one parameter fit model to the experimental data. And you can see that the model for R as a function of T lines over that perfectly. So that work is hopefully being submitted to ChemArchive at the end of the month, and you'll be able to look at that. Okay, so a bit of a summary. Sorry for such a whistle-stop tour there, but I wanted to get to questions if there's any time. What we've done active toroids, so non-point-like, we've changed topology. We've done fully 3D slender body theory for active colloids. So that's not point-like, that's 1D, sort of curled around. And we've looked at bubble, in this context, we've looked at bubble-propelled microswimmers in fixed shape. And what we're starting to do now is look at flexibility and shape change. So nearly out is the full chemo-elastohydrodynamics equations and a linear stability analysis, which Panayot's worked on when she was in my group, and the fully 3D slender body theory of active colloidal loops and knots. So we can do a trefoil knot, a slender trefoil, or any slender toric solenoid that you like to come up with, which is pretty cool. And still to do are extensions of slender phoretic theory that incorporate filament interactions, boundary interactions, finite Damm-Kerler number, lots of extensions, crucially the suspension dynamics, numerical implementation of our chemoelastohydrodynamics, which should be fun when we get that working. And finally, these shape transforming microswimmers, which we're now sort of starting to build experimentally. So that's all I wanted to say, really. And yeah, thank you for listening. And I'm sorry for talking at 100 miles an hour. I just wanted to get everything done before my my lecture.
Great, thank you, Tom. So would you say you have about 10 minutes of questions?
Yeah. I've
Okay.
got 10 minutes.
Okay, great. Anybody have questions? You can just unmute your microphones.
So maybe I can start, Kathy.
Yes,
so thank
please.
you very much, Tom. It was very interesting. Okay, as you say, there are many different things and many different stuff. So I'm not really, I'm not working in the field. I'm just wondering for some general questions. So the first is when you get, if you want to compare, let's say, your results with the real systems. So
Yes.
do you need somehow to map material parameters, for example, bending rigidity, or other parameters related with the specific systems?
Yes.
And where can you get the value of these parameters from?
Things like bending rigidity, materials are generally quite well characterized, these hydrogels, particularly if you're buying them from a shop. If you're making them yourself, you have to do characterization experiments. You can get things like bending rigidity from atomic force microscopy, generally. One of the big weaknesses of this area, which we're trying to shore up, is that the theory does not compare very well to experiments in general. So there's this very nice sort of theoretical framework, and it's not that the theory doesn't compare well to experiments, it's that there are insufficient there's insufficient talking between theorists and experimentalists in order to so that's what I'm sort of trying to do now with this bubble propulsion with Juliana Simchin. But yes, I think one of the approaches in order to improve this would be to start looking at a more multi-scale approach numerically. So I believe in this field we need to start incorporating molecular dynamics into simulations, and Amin Ramat, my postdoc, has started work on that aspect of things. But there's a massive load of work to do to bridge length scales in a way that will allow us to properly map parameters from experiments to theory.
So they are definitely very challenging systems for the multi-scale modeling. So we're working quite a lot on this aspect. So we can discuss, let's say, more probably about
it would be really good.
I think that they are very difficult systems to start from the atomistic level, let's say, or the microscopic level.
One of the issues that we're having is that in the classic continuum theory, you have a particle of around 5 to 10 microns, and the interesting stuff happens in a layer of 15 nanometers.
Okay. So if we assume that everything happens only in the interface, then it's okay. This is accessible. There are such scales that they are accessible.
Yes.
Again, from curiosity, are there well-controlled experiments on that system?
Are there what? Sorry, your
well-controlled experiments, well-controlled experimental data, let's say. Because I suppose that it's equally difficult or even more to have well-characterized experimental data for such systems.
Yeah. So the short answer is no. But I worry about saying that short answer because experiments are extraordinarily hard to do this, and I don't want to be the theoretician that complains that there aren't a suitable set of experiments for me to compare against. But no, the short answer is no. What this needs is a theorist, someone who does molecular dynamics, and an experimentalist to sit down together at the beginning and plan a set of joint experiments. To be honest, plan a set of joint numerical, theoretical, and actual experiments, and plan a parameter space to explore together. And it needs something big like Horizon Europe money.
Yeah, that could be that's a very good idea. And one more, I think the last, just since we don't have a lot of time, I'm just wondering, you saw in the chemistry that you have polystyrene, for example, nanoparticles in some cases. So you have polymers. in real systems. I mean, there are polymers. So how important are viscoelastic effects in your model, which I assume you don't consider them? So are they important or not?
Not terribly. So do you mean viscoelastic effects of how the shape? I was
thinking, yeah, memory viscoelasticity. So you have, let's say, I mean, of course, you get a Newtonian, more or less, solvent.
So the solvent
is Newtonian.
Is Newtonian.
I'm just wondering for the particle, if it is not, if there is, let's say, internal freedom in the polymer, in the nanoparticle, then you might have effects because of the viscoelastic response of the polymer.
Yes. So this is the fun bit. There are some very interesting dynamics which we've predicted but haven't been able to see yet because the experiments don't exist, and we've only predicted them on the back of an envelope. But essentially you can get spontaneous buckling for a start if you have a sufficiently flexible filament, and then what you can think about is, well, how does a suspension of spontaneously buckling filaments behave, which is a really cool thing. Also, if you have something spontaneously buckling, does it then form a translating mode? So do you get spontaneous translation via a buckling instability? Do you get oscillating dynamics? So is buckling, are there sets of parameters where buckling is suppressed by the confinement effects of the curvature? And so you might engender some kind of flapping mode behavior, or you know, these sort of, for instance, you could imagine something tethered to a floor which had an active component at the end and sets up some kind of periodic oscillation. All of this is possible, and all of this I'll be exploring mathematically over the next 5 years. But you know, it's that there's so much work and not enough postdocs always, and you know, it's hard to find people like Panayota. So
we're really lucky here. Getting people like Panayota.
Yeah. So in the short answer is yes. The viscoelasticity behavior of probably not in donuts, but when you go to these filament structures, it will become important to drive some very interesting dynamics, which we've theoretically predicted, but don't have the experiments to show yet. Okay. But those predictions aren't out.
Yeah. Yes.
Yeah.
Thank you. I think we will have the chance to extend this discussion. Please.
Yes. If there are any other questions, we've got sort of 3 minutes before I need to I need to go and teach a bunch of fourth years.
I think it's maybe best that you have a small break before your lecture, and we could possibly arrange for another seminar in the future.
Yeah,
hopefully with you present in Cyprus.
Yes, that would be lovely. We'll have to run it by my wife because I suspect she would.
She would come as well.
Yeah.
bring them all here.
Bring the whole family.
That's always the right solution.
Okay, thank you so much for having me, everyone.
Thank you very much.
Thanks, Tom.
Thank you very much.
Thanks, Tom.
Bye-bye.
Bye, everyone.
Bye-bye.